Okay, we're going to start because we're going to have a lot of time. When we see what else comes in. We have this is the first, for those of you who did not, this is the first lecture, okay, of the Advanced Mobile Product for this year. We have 13 speakers. They are all online, and so Srikant is the first one. A lot of effort tried to do, a lot of good people. So hopefully you will help in managing this, because every Friday now we're in direction at 11 every year. And this is online now. Today we're very happy to have with us Dr. Srikant, who is a professor at the University of Illinois. He holds there the Frederick and Elizabeth Nearing chair. He's also a research professor in the Coordinated Science Lab. He's been here several times. He's a very distinguished researcher in many years studies papers in communication networks, stochastic process, and queuing theory. He's the author of the book on mathematics of internet congestion control, which made it clear why some things were happening and made some of the models much more reasonable and analyzable. He is also the author of the monograph Network Optimization Control. He's a fellow of the IEEE. He's a distinguished lecturer of the IEEE Communication Society. Today he's going to talk, I'm glad to see some control people in the audience, about something that should be of interest to both communication network people and control people. He's going to talk to us about state-space collapse in the drift condition.
Thank you, John. Thanks for inviting me. So the title of my talk is State-Space Collapse by Drift Conditions. This is joint work with Attila Lyapunov, who's at Ohio State University. So I'll clarify what state-space collapse means. It's sort of a fancy term that probably is used for something pretty simple, but it's an interesting term. Okay, so what's the goal here? So traditionally, it is, I won't say relatively easy, but it's possible to design algorithms that sort of maximize the throughput in a communication network. That is a bit easier than actually showing that the policies that you get out of this, trying to maximize throughput are also minimizing delay or have good performance in some respect. Okay? So establishing the optimality of scheduling policies and routing policies, generically I call them control policies for communication networks, is quite difficult. Okay? So it's, you can set up a Markov decision process and try to get the optimal solution, but it's very difficult to solve. So what you typically do is come up with a policy that maximizes throughput, but also try to show that it has good delay performance. Okay? So typically these policies are not delay optimal, they don't minimize delay, but they have an appealing property that they minimize delay in what is called a heavy traffic regime. So what happens is that when the arrival rate to the system gets very close to the maximum capacity, the system, maximum rate at which traffic can enter the system, so the arrival rate gets close to the capacity of the system, certain remarkable simplifications arise. Okay? Essentially you can show that up to some error, which is essentially like a Taylor series, up to some error, the behavior of the system can be described purely in terms of first and second moments. And the way to capture these is to show that the arrival process and the service processes in an appropriate limit look like Brownian motions, and therefore everything can be described in terms of first and second moments. And in this Brownian limit, you can show that it is delay optimal, meaning that the delay that you see under the policy that you're interested in and the delay that you see under the optimal policy, which you cannot compute, these are not very different. Okay? The techniques used to establish these results rely pretty heavily on weak convergence theory and a lot of pretty deep mathematics. And so what I'm going to show today is that the same result, I think this has been something I've been thinking about for 7 or 8 years, and finally we managed to show this last year, that you can prove this using very simple Lyapunov arguments that you can teach in first class in random process. Okay? So basically the idea is, what I'm going to show is that from basic queuing theory we know that if the arrival rate gets close to the capacity of the system, so rho is a parameter that captures how close the arrival rate is to the capacity of the system. So we know that the queuing delay blows up as 1 over 1 minus rho. So what I'm going to show is that for certain well-known policies, the queuing delay blows up as 1 over 1 minus rho, some constant over 1 minus rho. And the best lower bound that you can obtain is also form that same constant divided by 1 minus rho, so that the two are close to each other. I'll give more precise descriptions of these things. So the basic idea here is to show that this Brownian limit-based diffusion limits or diffusion approximation-based optimality results can be established using simple Lyapunov techniques. So please ask me questions. I only have 30 slides, so if you don't ask me questions, I'll be done really, really fast. So interrupt me and ask me questions, okay? So I'm going to use a very simple motivating example, and if I get through with this, then I'll do a slightly more complicated example to illustrate my point. I'm going to take a very, very simple example that whether you work in communication networks or not, hopefully everybody should be able to understand. So let's think about how you're served when you're checking into at an airport, for example. Okay. So typically, what you have is you form a single long line, which is like they put these barriers, so it's like snaking around, and then there's a bunch of people serving you. And when the first person the first server becomes available, then they just beckon the first person in the line, and then you go and then you go get served. This is essentially the most efficient way to serve, because this will minimize the queue length. Because what happens is that whenever there's an idle server, the server is going to be used, right? So that is why it's good to form a single line, right? So whenever an idle server whenever a server becomes idle, it immediately gets utilized if there's anybody waiting in the line.
So the information pattern here is that the server only knows that it's essentially finished serving the customer.
Right. So here global information is available. So they can look at the queue and then just basically say that the first. Yeah.
But it doesn't care what each of the customers in the queue will require from the server.
No, at this point, yeah, no, yeah. So yeah. That might matter if the servers are very different and in some manner if you can match the jobs. Let's just pretend that the servers are all similar. Yeah.
When this was established, actually, it was a big fight. 10 or 12 years ago, even more in airports and other places, stores. Why was there seen two versus one of people in the banks with line around big fine?
Right.
And there was somebody, who went to banks in California and said, no, it's stupid, let's make one.
Right.
And they didn't buy it for about a year.
Well, I think part of the reason they don't like that is that in realistic situations, if you have 10 servers and if you have a common queue, the common queue might appear to have 50 people. Whereas individual queues, you break them up, it looks like you only are waiting behind 5 people. It's totally psychological. So for that reason, people like to have separate queues. On the other hand, if you go to Best Buy, this is interesting. They have separate queues. If you go to Best Buy, they have separate queues normally, but during Christmas time, they make it a single queue.
But Armand's question is also relevant, because if there are separate queues and you look and see whose grocery basket is full, then you get in some other.
That's right. So that's the next thing that
information is available.
Right. So the next type of model, I mean, this is what you see in grocery stores typically, is you have a separate line for each server, okay? And the way you typically join this, so here the server is not asking the first person to come up, or they might ask the first person in their own line to come up. But typically what you do is that as an arriving customer, you see how many people there are in the line, okay? You might in addition see the number of items they have, and then you join the shortest of these steps. Right, exactly. So that's the second policy, okay? And this, again, is efficient in a grocery store, because what happens is that sometimes what can happen is that even though you're forming separate lines, but one of the lines gets empty, and then quickly the person just moves over to the other line. So you keep all the servers occupied at all times, right? But an interesting question is, in a communication network, so that policy is called join the shortest queue. So when you're arriving, you join the shorter of the queues, and that's called join the shortest queue. I mean, that's, but then in a grocery store, you don't just stop at joining the shortest queue. You also defect from one queue to the other when you see the other queue getting shorter, or it might get empty, for example. In a communication network, on the other hand, let's say there are two routes between a source and destination, and you get some information. Let's say you get feedback on the congestion on these two paths. So you get some information about maybe the delay on this path is larger than the delay on this path. So what you might do is that you might send your packet along the less congested path. But unlike in a grocery store, suddenly, this is a probabilistic system, right? It's a random system. So when you release the packet, you think that the delay is less here, but then it's possible that this path suddenly gets free because maybe the service times of these packets are smaller. And so, but you cannot recall the packet and put it here. Unlike you can do it, like what you can do in a grocery store. In a grocery store, the minute you see one line getting empty, you defect, right? So you can't do that here. The question then is, even though we don't defect, is this policy still optimal or close to optimal? Clearly it's not optimal, because occasionally you will have idleness in this policy. A server will be idle because its queue becomes empty, whereas some other queue is non-empty, and so it could be serving somebody else, but it doesn't. So the question is join the shortest queue still optimal? Okay, so this is a interesting question, and this is the simplest model that I know of where you can show that a control policy is optimal in a heavy traffic sense. It may not be optimal normally, but it's optimal when the traffic is heavy, in a sense that I'll describe precisely. Okay, so the regime that I'm going to consider is one. So I'm first going to analyze the join the shortest queue policy to give you the basic idea behind the methodology that I'm going to propose. So you have L servers. So I'm going to call the service rate mu1, mu2, mu(l). And for simplicity, I'm going to assume these are all, the mu1 could be the number of packets that this server can serve per time instant. Mu2 could be the number of packets this server could serve each time instant, and so on. And lambda's arrival rate is the number of packets per time slot is arriving. I'm interested in the regime where the arrival rate is close to the capacity of the system. So in other words, if I use epsilon to denote the total service rate minus the arrival rate, I'm assuming that epsilon is a very small number. Okay, how this plays a role, we'll see in the next one. So this is the regime that I'm interested in. This is what in the probability literature people call the heavy traffic regime. Okay. So the classical result is by Foschini and Gantz in 1978, proved that join the shortest queue is heavy traffic optimal. Okay, this is the same Foschini who 15 years later did a lot of work on MIMO systems. It's quite a versatile guy, just worked on completely different things, and a remarkable person. So what he proved, what Foschini and Gantz proved was a result like this. Okay, some of you I'm sure understand what this means, but I bet a majority of you cannot understand what this means. This is the point of my talk. Okay, this is the point of my talk. So basically, the heavy traffic literature proves results of this type. You scale time, you scale space in some manner, and then you let epsilon go to 0 and you have optimality. What does this mean? Okay. What does this mean? And so essentially, the scaling of space and time allow you to use results from Brownian motion theory and establish optimality in the sense, meaning that if you let epsilon go to 0, then the trajectory as a function of time is the smallest under join the shortest queue compared to other policy. What does this mean? Okay. Really, what I'm more interested in is I would like to be able to compute quantities like this. So expected value of Q1 plus Q2 plus QL. I want to show that this is minimized in some sense. I mean, this in steady state. So let's say this expectation is taken in steady state. Okay. Then I would like to show that this is minimized in steady state. And this is what essentially they're trying to show here. Okay, but it's much harder to understand what this really means. Okay, so what I'm going, and the techniques are harder and everything. So what I'm going, and you can say something about steady state, but this requires the interchange of limit, because typically steady state means t going to infinity. Here they let epsilon go to 0. You're interested in t going to infinity first and then let epsilon go to 0, but what they actually show is epsilon going to 0 and then t going to infinity. And doing this interchange of limits is not a trivial task. Okay, so very, very few papers attempt this. Okay, I'm going to show you a technique which completely circumvents all of this. Okay, so this is the point of the talk. So this is what I'm going to show. I'm going to show that we know that the expected value of the total queue length will grow as 1 over epsilon. We know if the arrival rate gets close to the capacity of the system, and if epsilon measures the difference, we know from basic queuing theory, the total queue length has to blow up to infinity. And it blows up at rate 1 over epsilon. What I'm going to show is that there is a universal lower bound, which is of the form some constant over epsilon. And our policy, join the shortest queue policy, actually achieves the lower bound up to some error term. So it is asymptotically optimal in this sense. So this is the sense in which I am going to describe heavy traffic optimality instead of this. This is the sense in which people who use Brownian limits argue. Okay, I personally think that this is much easier to explain. This is much easier for people to understand what this really means. So as epsilon goes to 0, the leading term on the left and right hand sides match. So this is what I call heavy traffic.
Just repeat
Yeah.
the assumption for the system you're considering.
Okay, good. So the problem I'm considering is this. I'm considering a set of L parallel queues. Customers arrive, and when the customer arrives, joins the shortest of these queues.
Exponential service.
This is discrete time, we're just assuming IID service time. So that each time slot, the number of packets we can service IID. And the number of arrivals in each time slot is some random variable, which is IID. You can extend it to more general cases, but that's the simplest case that we're going to talk about. Okay? And for this, what I want to show is that join the shortest queue is optimal. It's heavy traffic optimal. And what I show by heavy traffic optimal, what I mean is that the expected queue length has a lower bound which no policy can beat, and join the shortest queue gets the first term, the expansion of the expected queue length, and the join the shortest queue matches the lower bound. Okay. This is, and we'll show this using very simple drift arguments. Okay, so using sort of the Lyapunov type argument, and in fact, so this is. So in fact, we show that it's not only the first moment, but all the moments are.
Just to trying to say the narrative, so the K1 is essentially determined by the JSQ, or is achieved by the JSQ.
Right.
Otherwise,
But there's a lower bound which is K1, which is universal for all policies. No policy can do better than that. What I'm going to show is that JSQ actually achieves that K1. This is upper bound corresponds to JSQ. The lower bound corresponds to any policy. Okay.
now what happens if the controller you're using is not in use in your ergodic marker chain? Therefore, this may not make sense.
This moments might exist. So in all the cases that I'm assuming we can show that the steady state moments exist. For the type of control policies I'm looking at.
So all the policies must have a steady state.
Yeah, that's right. Yeah. So the lower, you mean for the lower one, right? Yeah, right.
But you could have had a weaker statement with a super limit.
Correct. Yeah. Actually, you can write some of these things with lim suit and make it more precise. Yeah, exactly. That's true. But then in which case, I have to also probably write summation k equal 1 to k over 1 over k, instead of, time averages and so on.
Possibility.
Yeah.
Do something a little
You can make statements like that too, but let's just say for simplicity, I'm going to assume that everything is ergodic. Not only is ergodic, I'm going to assume the moments exist. Steady state, yeah.
Now,
Sure.
we know counterexamples that for exponential service of continuous time, join the shortest queue, not asymptotically, but moments, is null.
Yeah. So this is only asymptotic. Yeah. So the preface to the talk was, in general, the control policies that we have are not optimal. Join the shortest queue is not optimal. Max weight, you have papers that Tassilas which shows that for this linear networks it's not optimal, but we show that max weight is also actually heavy traffic optimal. So it's not optimal it's not in general optimal, but it's optimal in a heavy traffic sense. That's a good point. Yes. Okay. So the basic idea, the reason I chose the join the shortest queue example is that everything is relatively easy to illustrate in this example. So what is the best lower bound you can get for the join the shortest queue example? So have L parallel queues. Okay. The best thing that can happen is all the servers pull their resources together and act like a single server with the total service capacity summation of S7, right? Same arrival process, but the servers pool the resources together, and so in fact, this is what's called resource pooling. People use the term resource pooling. So resource pooling gives you a lower bound. Okay, so consider a queue, the same arrival process, but the service process is just simply the sum of the service process, all the L servers. Yeah. So what I want to do is I want to obtain an expected queue length for this queue, for this lower bounding queue, and so that will serve as expected as a lower bound for the expected queue length for join the shortest queue. And the way you get the way you get the lower bound is in steady state. I mean, assuming these quantities exist, which you have to establish, I mean, which are not very difficult to establish. What you show is that the expected value of q squared doesn't, you know that the expected value of q squared doesn't change with time. I mean, that's what steady state means, right? So you set the expected value of q squared at time k plus 1, you put an expected value of q squared at time k. Okay? You do this, and then immediately it gives you a lower bound. There's a lower bound. The reason there's a lower bound is because so the q dynamics look like this, right? Q at time t plus 1 is q at previous time instant, plus the number of arrivals, minus the amount of service that you provide. And there's some unused service. The reason there's unused service is that the total queue length is less than the amount of service you can provide. Some of the service is wasted, and this is hard to characterize. Okay? So by dropping those terms, when you set these to equal, you get a bump.
And the SK is a discrete random variable.
Right, SK is some of
No, you can say. Yeah, SK is okay. And it's ID across time, I presume.
Correct. Yeah.
Okay, and UK is what's left over.
Right, exactly.
Okay, so.
Okay. So this gives a immediate lower bound on the expected queue length. It turns out that the lower bound is just a function of the second moments of the arrival minus service cost. So here you start seeing a connection to Brownian literature, because if you do this for higher moments, so you can get a lower bound for the second moment, third moment, fourth moment, all of those lower bounds remarkably depend only on the first and second moments. So this is why people who work in the diffusion approximation literature sort of surmise that maybe there's a connection to Brownian motion here, right? But I don't want to use that connection. I want to keep it as simple as this. This is trivial to drive.
Where did the epsilon come in from the previous equation?
Just that
What did you get?
the epsilon is the difference expected value of this.
The scale here.
Yeah, the expected value of SK minus expected value of AK is epsilon. And when you expand this out, you'll see a term where they have expected value of SK minus expected value of AK. And that will show up.
Excuse me, I think it depends, but the left-hand side has a minus. So how can it be greater than what's on the right-hand side?
Sorry, which one has a minus?
We had a 1/2 over 2e equal to minus a minus s squared.
That should have been a plus probably. Yeah. That should have been a plus. Yeah, thanks.
It is a plus.
I just want to make sure.
Yeah.
That's right.
That's right. It is a long one. Yeah,
I would have been another one.
right. Yeah.
Well,
Okay, so we want, so that's the lower bound. That's the lower bound. And we need to obtain a matching upper bound. We want to show that join the shortest queue, okay, actually achieves the same upper bound. So we have a lower bound that is true for all policies. So if you recall, the lower bound is obtained assuming that all the servers act together, right? So the matching upper bound should essentially capture the term, but without making these assumptions. All the servers don't act together, but the very fact that you're joining the shorter queue makes it appear as though the servers all act together. And the reason is that because what happens in heavy traffic, when the traffic is really, really heavy, and you're joining the shortest queue, essentially what it does is that it equalizes all the queues in some sense. So all of the queues either hit empty, approximately. The idea is to try to make all the queues hit empty at the same time, okay? Or they are not empty at the same time. So effectively the amount of idleness is very, very small. That's the basic idea. The question is how to prove this, and the basic technique then applies to, the main reason I was interested in this problem was to show something about the heavy traffic optimality of the max weight policy that you probably all know. That's in this max weight policy. But I'm just explaining it for JSQ here. And there the analysis is much more complicated because the geometry of the wireless capacity region is very, very complicated compared to this. But the essential idea is very good for that also. Okay. So this is the intuition. So essentially what happens is that in heavy traffic, And the idea is since we're trying to equalize all the queues, the amount of idleness is very, very small. Because so since if all the servers are idle at the same time, there's never going to be a situation where one server is busy and other servers are idle, which is the bad situation. Because if one server has 10 people waiting in its queue, then basically the other server should be helping out. And if they are idle, then that's bad. What the heavy traffic analysis shows is that the amount of idleness is very, very small. Okay? And so geometrically, so this is where doing this geometrically, I mean, there are other ways to prove this for join the shortest queue. But I'm going to show a particular way of proving it, which then carries over to wireless networks. Okay? So the main idea is that, so what are we trying to show? So we're trying to show that all the queue lengths become roughly equal. If all the queue lengths stay exactly equal at all times, then this is the optimal policy because they are all the queues will idle at the same time, will become empty at the same time. So another way to say this is that look at the vector 1, 1 and look at the queue length. Okay? So the projection is what is called Q parallel. The perpendicular component is Q perpendicular. I want to show that Q perpendicular is very small compared to Q. This is the big. This is what. So this is why people in the probability literature call this state space collapse. So the reason they call it state space collapse is that in many of these queuing systems, what happens is this vector Q is a very high dimensional. So in this case, it's just a 2-dimensional quantity. And if Q perp is close to 0, the system behaves as though it's a 1-dimensional system. So in general, actually, an n-dimensional system collapses to 1-dimensional system. Okay? So if you have L servers, L could be arbitrary here, so L could be 100, the number of parallel queues could be 100, or all the queue lengths become equal. So in heavy traffic, the system, a 100-dimensional system, acts as though it's a 1-dimensional system. This is the trick. Yeah.
My intuition tells me that, with the exception of very weird policies, all of the policies that are reasonable to have that problem. For example, if you randomly choose which queue to join, heavy traffic, why would that happen?
Yeah, exactly. So good question. So if you randomly join, what happens? Okay. So let's take the case.
Say 2 queues.
Let's take the case of 2 queues. If you randomly join, the row remains the same, right? So 1 over 1 minus rho is the queue length of each one, or rho over 1 minus rho is the queue length of each one. Okay? And you multiply that, so the total queue length is 2 over 1 minus rho. What I'm claiming is that it still remains as 1 over 1 minus rho. So the L queues, we get L over 1 minus rho, whereas I'm claiming that it's still going to remain as 1 over 1 minus rho.
Okay, maybe the random choice doesn't work, but I would think that this property is not unique to join choice.
Yeah, so for example, another policy that would work, but you have to take into account state information. So another policy that will also be heavy traffic optimal is that, so looking at all the queues, suppose you sample 2 queues, okay, and then route it to the smaller of those 2 queues. This will also work if the queues are identical. If the queues are not identical, then you actually need memory. Yeah, so it is actually, it is not that easy if the queues are not identical. Yeah. So is this clear? Yeah. Okay. So so the main point is to show that Q perp is small. So the whole idea here is that I'm going to show Q perp is small. And in what sense am I going to show Q perp is small? I've already obtained the lower bound that suggests that the expected value of the sum of the queue lengths is going to be of order 1 over epsilon. What I'm going to show is that in steady state, the expected value of Q perp is a constant. Okay? So compared to expected value of Q length, which is like 1 over epsilon, as epsilon goes to 0, this is practically nothing compared to this. So this is basic. So if you look at the Brownian literature, you will not get this intuition. Okay, so let me just say it. So this is exactly what's happening. In steady state, this is of order 1 over epsilon, and that is constant. But that is exactly what state space collapse means. Okay, so basically what we do, again, so there were many different ways to prove this, and I actually have, this was the 3rd proof that I came up with, and one of the reasons I did not publish it earlier was that I insisted that everything had to be done using Lyapunov drift arguments. Okay, and the reason for that is I just wanted it to be, there's a simplicity to it, and I wanted to make it. There's a large deviations way to prove this. There's another way to prove this, and so on. I wanted to prove everything using just a simple drift argument because it's something that we teach in the first course of control or first course. I mean, it's just there's a simplicity to it, and so I wanted to use this. And so basically, what we are going to show is that expected value. So look at a Lyapunov function. So the Lyapunov function is just a norm of Q curve. That show that I'm not going to show here, but what you can easily show in the context of JSQ is that expected drift, the change in this Lyapunov function, conditioned on the current Q length, is actually is a negative number which is independent of epsilon. So it doesn't become small at all. So in other words, the Q perp gets smaller and smaller, and the amount by which it gets smaller at every step is independent of how close the arrival rate is to the capacity. And this is the key. Because so in other words, the Q lengths are all very, very large quantities, but Q perp itself shrinks so fast, okay, that you can show that it remains a constant in space. So this is the basic idea. I didn't really show all the intuition here, but the basic idea in the case of two Qs, in the join the shortest Q policy, if Q1 is greater than Q2, all the arrivals go to Q2. If Q2 is greater than Q1, all the arrivals go to Q1. And if you just write out this expression, you can see that the amount by which it becomes negative is actually independent of the arrival, independent of the difference between the arrival rate and the service rate. It just actually is some negative number which doesn't go to zero as epsilon go to zero. So it's very easy to actually, when you write it out, you can easily see this. And
why are the two bullets implying the third?
yeah, that's why I said I didn't explain that intuition very well. Yeah, it doesn't. So
That's the crux, right?
right. Yeah. So let's think about it this way. Let's say Q1 is larger than Q2. Okay? So let's take this. So Q perp in the simple 2D cases of the form is Q1 minus Q2 divided by root 2. So let's just ignore the root 2 for the moment. So let's just say Q1 is greater than Q2. Okay, so then this W quantity is Q1 minus Q2, right? So let's look at let's just pretend it's a continuous time, but basic intuition is similar. So let's look at W dot, which will be Q1 dot minus Q2 dot. Okay?
And derivatives with respect to
Time, sorry, dWdt.
I thought that Q1 was already in steady state.
No, this is not the same. This relationship is actually at any time instant. Yeah, so
it's W, I see, I get you.
Yeah, this relationship, and from this you can say something about steady state, and I'll show you how you can say something about steady state. So this is Q1 minus Q2. Because Q1 has no arrivals, because all the arrivals are going to Q2, this is going to be minus mu2. This is the service rate of this first, minus mu1, sorry. And the second one is going to be of the form lambda minus mu1. So all the arrivals are going to go to Q2. So this is going to be of the form sorry? Right. So I'm just going to write it. So it's mu2 minus mu1 minus lambda. Okay. So let's take the simple case mu1 equals mu2. Okay. So then this is just minus lambda, which is different from, whereas epsilon in this case is 2 mu minus lambda. Whereas lambda is a much larger quantity. So this drift is strictly negative even when epsilon goes to 0. Epsilon goes to 0 means lambda is going to 2 mu. Okay? So this drift is negative, it doesn't go to 0 as epsilon goes to 0.
So it's not quite right to say independent of the arrival rate.
Sorry, independent. Did I say independent of the arrival?
Yeah, that's what.
No. What I meant was independent of how close the arrival is to the capacitor. Yeah, good. Yeah, thanks. Independent of how close, so it doesn't go to. So the main point is that this does not go to 0 as epsilon goes to 0. This is what I'm trying to say. Okay. Yeah, it's not independent of how close. It's independent of how close the arrival rate is to the capacity, to the surface rate. Thanks.
Kind of epsilon.
Independent of epsilon. Yeah. So the reason this result is useful is that actually Bruce had given me this paper about 15 years ago. He told me about this paper, and I have never been able to use it. And I was on sabbatical leave last year, and I was trying to prove this result. And I came across a paper by Robin Pimentel. I don't know if you might know, he's a mathematician at Penn. And I was trying to show, it was intuitively obvious to me that the drift being independent of epsilon must say something about the steady state moments. And I saw this paper by Robin Pimentel, and he had actually cited this paper by Bruce, and I realized, oh, I should go back and read that paper. And that was a beautiful result, which immediately, it's a remarkable, this is a two-line proof. Okay, so it's a really neat proof in the paper. I mean, I would urge everybody to read this. It's a really simple proof. Essentially what he shows is that if we have a drift that is less than or equal to some minus delta of some Lyapunov function, then the exponential moments for sufficient, I mean, there exists theta sufficiently small. For all theta less than or equal to some upper bound, you can show that the exponential moment is bounded by m, which is a function of delta. So the main point here is that the moments in steady state, the exponential moment of q per is independent of epsilon. It only depends, in this case, depends on lambda, but it doesn't depend on epsilon. Okay, so that's the main thing. So in other words, from that it is not very difficult, next step, to establish that the expected value of the first moment of the q length, expected value of the second moment, all moments of the q length, because the exponential moment is bounded, all moments of the q length are bounded. Of course, it's different moment, different bound for different moments, but they'll all be independent of epsilon. So this is precisely what I mean by state space collapse. So state space collapse means we know that I have a very established lower bound which says the expected value of the sum of the q length is at least 1 over epsilon. That's the lower bound. And we show that norm of q per is constant. So compared to this, it effectively doesn't even exist as epsilon goes to 0. Okay? So this is the intuition. So I start off by saying that the q lengths all roughly become equal, but they're not always equal, right? They're not always equal. So sometimes some q's are going to empty before other q's. But what this is saying is that the perpendicular component is going to be so small, so for all practical purposes if epsilon goes to 0, you do have this state space collapse, which means that the system acts as though all the servers pool their resources together, even though it is not like the airline model and it's more like the grocery model. That's what I'm saying. So the grocery model and the airline model are not very different in heavy traffic. Okay. So to actually establish the upper bound, again, we insisted on using Lyapunov techniques again. And so what we want to show is that all this, the sum of the q's behaves like a single q. So I'm going to use the Lyapunov function, the sum of the q squared, and to set the drift of that equal to 0. Okay? And this gives you an upper bound. So because the reason we use this Lyapunov function is that we expect the sum of the q's to behave like a single q. And so essentially the idea is that when you expand that, you'll get terms of, so this is where mathematically this is how we use state space collapse. When you expand the Lyapunov drift term in the previous page, you'll have terms like this. QLK plus 1 multiplied by ULK. ULK, if you recall, is unused service. So if the Q at the next time instant is non-zero, unused service must be equal to 0, because you're not using service only when you don't have enough to serve. So if the Q at the next time instant is non-zero, that means that all your service were used up and still there are packets left over in the queue. So this product is 0. The difficult thing is what to do with this product, where QL at k plus 1 multiplied by UJ at k plus 1. But that's not the state space collapse result. Essentially, what it does is that, so QL at k plus 1 can be written as QL minus QJ times UJ. Because we know that QJ, UJ is 0, so I'm just adding a 0, subtracting a 0 term from there. Now if you use the Cauchy-Schwarz, should be some square root somewhere. Yeah. Essentially what will happen is that this term is constant, and the unused service is very easy to show that it's going to 0. What did I say? J and L are different. J and L, yeah. You can see I haven't given this talk very often, so I'll correct all these typos next time. So that's the basic idea. In fact, the same methodology can be used to establish that join the shortest queue minimizes. So basically the result is expected value of the summation Q length is between K1 over epsilon plus, and is upper bounded by K1 over epsilon plus some additional term. Let me just call K2, it could also depend on epsilon, but that's just for simplicity. So if I multiply by epsilon throughout, essentially this term is going to 0. So multiplied by epsilon, join the shortest queue minimizes the first moment. What I'm saying is that the same methodology can be used to show that it minimizes actually every moment. So as long as Q is scaled by epsilon, because Q has to be of the order of 1 over epsilon, so of course you cannot compare to infinities. So therefore you have to multiply it by epsilon. Q multiplied by epsilon, you can show that every moment
Is there a possibility of resolving the stochastic order sense?
Yes. This is basically what the Brownian. So, okay, what happens is that this. Okay, so what the Brownian motion result tells you that every time instant, actually the scale Q length is the smallest possible. Okay, so but I don't know if anybody has proved that in the limit as so if they first let epsilon go to 0 and prove this for any finite time t. Now your question is about steady state, so I want to actually let t go to infinity.
I mean, it's true for every t, it's true for any sense.
No, but the problem is the Brownian motion limit itself is established over only over uniformly over compact sets.
Yeah, but then I would argue that if I use the same trick you use, get an upper bound, which is essentially reducible to single server Q.
Yes.
And then you can use the classical.
Exactly. Okay. So for this particular problem, for JSQ, yes, you can do it. Yeah, that's right. For JSQ, you can do it. Correct. For JSQ, you can do it. But my question is, I don't know if that's easy to establish more generally. So for join the shortest queue, people have done it. And for there is a heavy traffic result for Jackson networks that I mentioned earlier. Gamarnik and Ziggy have done it. And there's a recent result by Sasha Stolyar and Elena Yudovina, who's a student of Frank Kelly, who have done this for yet another model. But I don't think it captures all of the models that I can have using this. Yeah, sorry.
So the essential thing here is to make sure that none of the queues will empty while there is.
Yeah, exactly.
For any policy
That's
which
right.
has grant,
Yeah,
should
correct.
do, just by
Correct.
stochastic comparison of the
Correct.
two. So I would have a policy that says just join anything arbitrarily, and the first queue that crosses a threshold downward, then you start putting, you don't allow anything to go below threshold before you start putting the next task forward. So there would be
The threshold has to be.
more than the number of servers, because you could have a K customers simultaneously finishing service. So if you make the
Yeah. So I'm not saying that there are definitely other policies in the context of JSQ that would work. So
yeah, I understand, but it appears that this shows a very good property of the joint shortest queue, while that property is shared by many others.
Correct.
Because the essential thing is not to join the shortest queue,
Right.
it's not
in fact, actually, it's not enough to just have a threshold. You have to actually have a threshold that is actually a function of the arrival rate minus the service rate to actually get the 1 over epsilon correct scale.
If it is discrete time,
In discrete time, when you have multiple
then you can have just K.
the multiple packets can arrive here. I'm not restricting myself to one arrival per time.
Yeah, but so, okay, so the moment any Q reaches the threshold K, then
What is
all the
K?
arrivals, K is the number of Qs.
But you could have multiple packets being served in the same time slot by Q and all that.
Or by a single Q.
Yeah.
But you take value of
Yeah,
that's
so,
just the
but it
threshold.
could be infinite, for example. So you have to be careful. Yeah. So that's what I'm saying. So actually, in general, if you make it some function of epsilon, then it does work.
Yeah,
Yeah.
it can be adjusted, but
Right.
I think the essential thing to be illuminated is that's what you
Correct. That's exactly what.
Then the
Right.
policy and the pooling of resources will have the same.
Exactly. So So basically threshold type policies will also work. But what I'm going to, the main point of this is, okay, so let me finish this and then go to that. So the basic approach is 3 steps. So you have a lower bound. You first establish a lower bound, and then you establish state space collapse, and then you establish upper bound. Upper bound uses state space collapse and prove the lower bound equal to upper bound. So the main thing which I am interested in is wireless networks. Okay, here policies that are even throughput optimal are not obvious. There are not that many policies outside the class of max weight that are throughput optimal. What I'm claiming is that the same technique can be used to show the throughput the delay optimality of max weight algorithm. So this is the main. So here it is
For the sum.
for some complicated version of the sum. It's not obvious. So this is a very general wireless example. So let me, the next 10 minutes, let me tell you what the result is for wireless network, which is really the main thing.
You're showing delay optimality of what is that?
Okay. I'll get to it in a second. Exactly. So this is a wireless example. So you have multiple queues. Okay. So each one is a wireless link, and there is interference, which tells you that only a subset of these queues can be operated at each time. Okay. So a simple example might be in the 2Q case. So there are 2 queues here, and if, for example, if you decide to only transfer packets from Q2, then Q1 gets rate 0, Q2 gets rate 2. Otherwise, Q1 might get rate 3. I mean, it's made up these arbitrary numbers. Whereas if you decide to operate both of them, then you get certain intermediate other rates. So the capacity region looks like this. So the classic result due to Tony and Leandros is that the point that you pick on this capacity region should maximize, so where mu is the service rate that you provide to each user, summation of mu and QL should be maximized. Okay. Now it is quite non-obvious as to what even resource pooling means in this network. There is no resource pooling. I mean, different sets of resources. Okay, so here everything that I said previously for the very simple model for which there could be other algorithms and so on which also achieve this. Everything works for this, and here this is completely non-obvious what resource pooling means, what the lower bound means. Nothing is obvious in this.
Because it's a region, you don't know what is the criteria. This is a whole region, so it's not a single. I mean,
So what is it? The criterion is, so I might be interested in something like this. So minimize, for example, something like this.
That is, I mean, yeah, that's very worthwhile. I'm not disputing that, but obviously this chooses a narrow slice of what the problem is, which is it's a more complicated question that one should ask. We have a region. What is the best point of operation in this capacity? For example?
Well, I mean, no. Let's say the arrival rate is fixed.
Yeah, there is no answer to where you would like to operate.
No. Arrival rates are fixed. Arrival rates are exogenous here. So somebody gives you the arrival rate.
If the arrival rates are fixed, then you don't necessarily know what is the shape of that region. So this capacity region assumes they are saturated queues. So it's not.
No, service. You're talking about service rate or arrival rate. I'm talking about. So this is the capacity region is just a function of the service rate.
Yes.
Capacity region is a function of the service rate.
If you allow arrivals, that is not necessarily the region of stable operation.
I'm talking about within the region of stable operation.
Yeah, but it may not coincide with the region of the service rates. I mean, this is one of the outstanding questions. Does the capacity region equal the stable region
It
when
is.
you have random arrivals? No, they're not necessarily the same.
No, it is.
That means
This is not aloha or anything like that. I'm not talking about aloha.
No, there are cases where they're not the same.
I mean, you're allowing some form of coding or something like that. For this, I know for sure it is. I mean, so take this example, where these are the only 4 possible rates.
Yeah,
Service
straight from straight.
Yeah. So I'm talking about practical wireless networks where I know these are the 4 possible rates that I can choose. Then I know that the capacity region is exactly this. So anything outside cannot be stabilized. So by this law of large numbers, you cannot stabilize it.
Yes, you cannot stabilize it. However, you could have capacity namely bits per second.
That's different, yeah. So information theoretic capacity of this could be, I don't know what that is. So I'm talking about stable operation within an inner bound to the capacity.
What should be the arrival rate so that I can do the
Yeah,
even those
exactly.
service rates?
Yeah.
But again, even then, you don't know what is the objective and which one will you pick of those four, unless you decide I want to.
This is what I'm saying is that this policy is known to, as long as the arrival rate lies within the capacity region, this policy stabilizes.
Yeah.
What I'm saying is that this policy has an additional remarkable property, that it also has some minimizing delay properties. That's
Yes,
what.
but the delay properties in the sense of a single function of those two sizes.
Yeah, exactly.
So
Exactly.
it's like a total delay. Wait.
Yeah, wait a bit. Yeah, exactly. Yeah, exactly. In fact, what one can show is that even without weights, it does the following. It actually minimizes this quantity. Yeah, but still a particular. Yeah.
My point is, these two delays 2 and 10. Is these two delays better than or worse than some delays being 11?
Yeah. That I don't know.
Yeah.
But what you can do for that is, of course, you know all this. I don't want to tell you this. You can put a weight here.
But it still looks at a single slice.
Well, I mean that's all you can do, right? I mean, so when you have multiple queues, you have to have some weights on the queue length and decide that this
If
is
you want to have a
Right.
single utilization.
right. And then for different weights, then you have to choose the weights differently. So if you want to give priority to one queue, then you have to increase the weight on that queue, for example.
So, make sure I understand. So the QLs will depend on the selection of the views.
No, sorry, here QL is just simply the queue length. Current queue length. Yeah. Current queue length will depend on what you chose in the past.
This is not a steady state.
No, this is the policy. So what I'm saying is the policy, the capacity achieving policy in this case is one where you actually take the product of the current queue length multiplied by the service rate. There are many possible service rates you can choose. The Tassio reciprocity policy says that choose the service rate that maximizes this weighted sum, where the weights are simply the queue lengths.
Instantaneous.
At each
So
time.
this is a transient policy.
This is the transient policy. Yeah, this transient policy has the property that I'm running out of time. Essentially, what you can show is that let me just show you
You're
that.
complaining you only have 20 slides.
That's good. I'm glad you guys
I'm
are
very sure you didn't get through that.
We made sure that
That's right.
we didn't run into
Actually, this is the third time I'm giving this talk, and I've never gotten through any of the 30 slides ever, which is good. I mean, it was the best kind of talk that you can. Yeah, exactly. That's good. So because I mean, otherwise, I mean, I'd rather have you do this than finish in 30 minutes and have no questions, right? So this basically you can prove the result of this type here, and here it's a lot less obvious what resource pooling means. Okay, so what is it? So that's something that I unfortunately didn't have time to get to. So what is the lower bound even is not obvious, but then
Because
essentially.
you link this delay because you link the delay as a function of the queue.
I just queues at this point. I mean, of course, you can make it. You can link it to delay by using Little's law. Things like that. Yeah. So basically, some weighted version of the queue length is actually minimized in the heavy traffic sense.
Just to make sure, again, going back to the earlier question. So your max weight generates the action according to what you had on the previous slide.
Right.
One clock.
Not what I had applied, but he had.
One clock at a time. So the result is, okay, let's assume that it's stable.
Yeah.
So you construct this expression there that is this nth moment,
Right.
and your claim is that as epsilon goes to infinity,
As long as it's zero, as time goes to infinity.
so regardless of what C is, it will.
No, it's not what regardless of C is. So C has a particular meaning here. So the correct state. So from this you can infer the following statement. This is the topology independent statement that you can make. The max weight algorithm always minimizes the second moment of the queue. In steady state.
And so what is the C then?
The C is unfortunately, yeah, I can talk to you after. C is topology. This is the main result. So let me conclude. Yeah, so I think these results not only are useful only in steady state, but I think the way, I didn't get into all the details, but actually even when epsilon is not equal to 0, actually the results provide an upper and lower bound. So you can have bounds on where the Q lengths are going to be. And I believe it is a very general technique that applies to lots of different problems, not just routing or scheduling problems that I talked about today. But I think the most exciting thing to me is provides a moment-based interpretation of state space collapse that I've not seen before. Okay, so the state space collapse is a technique that people. Do you have a question about it?
Yeah, I just want to ask you, is there some robustness to the policy? So if a policy minimizes that cost function or some n, any policy, is it true that it also minimizes for all rural n's? Does it follow from your method provisions?
In the examples that I have, it seems to, but I don't know if that is a fact. That's a good question. But my conjecture is that many of these policies have probably a similar property, because essentially what happens is that only the first and second moments matter to establish these things, and then on the higher moments just depend on the first and second moments. I mean, this is the sort of the connection to the Brownian motion literature, because of you approximate these by Gaussian process in the Brownian motion literature. It not only proves optimality at the first moment, it proves that in steady state you have an exponential distribution at Q length, and that's the smallest distribution that you can have. I mean, that's a conjecture in general, but in Armand's question, I mean, that's a sort of a stochastic comparison kind of result, which can be established with some difficulty in some special cases. But the general conjecture is that that's probably how it is for most policies which are heavy traffic optimal for the first one, probably also heavy traffic optimal for the higher one. So I don't know, I don't have proof of this.
When epsilon is finite, we can get different bounds for the values of words.
Correct.
Set the three to less or something.
Correct. But the main thing is that what I'm trying to say is that I want to get a bound that's of the form k1 over epsilon on both sides. Otherwise, if you just want to get bounds, so there are two things here. One is I'm getting bounds, and also the bounds are getting tighter. The upper and lower bounds are getting tighter in heavy traffic. So yeah. So there are many interesting open questions here that I'll be happy to talk to you separately if you're interested. But I think that this is very interesting, and I've talked to other people who work in this literature, and they were somewhat surprised that we have this information state space collapse. So just sort of I think it brings the technique closer to a lot of people. I think the Brownian technique was had a very esoteric set of tools that they use, and it's not accessible to everybody. And I think this makes it accessible to a lot of people. Thank you.
We have time for, let me just say, we have time for more questions, and also 3 o'clock, I believe, right? 3 o'clock. 3:30 to until he leaves about 4:15. We are going to be in the little conference room in the building in front of the Williams, where the center is, for an informal roundtable, so you're welcome to come. You can have more informal discussions. I'll make sure the door is open, so you don't use it everything. So more questions?
Yeah.
It's a second moment of theory.
Right. I mean, depends on the first and second moment of arrival in service process. Yeah.
What happens when, for example, again, when someone argues that it's not realistic or whatever, but just for the pleasure of considering the issue, what happens when, in the second moment, for example, when you have heavy flows?
I wanted to ask you this question actually. I don't know the answer to it. Yeah. I don't know the answer to it. I was going to ask you this question.
Since I have all the experts in the room, can I ask a question to all the experts? What's the best result for throughput versus delay trade-off for reliable? Is there anything?
Best in what sense? There are results.
Is there anything good trade-off?
Oh, you
Because
just
he mentioned that I take the maximum weight out of my put out, and then for some of them I can actually find good properties of delay. But
for fixed throughput, you can say bounds with delay, vice versa, but I don't know what best means.
I think he's interested in the multi-hop case. The multi-hop case is a lot harder to say.
anything that you would consider a good trade-off result, forget best. Sorry for my stupid language. Knowing that you are in the room, you will ask the obvious question, what's
For
best?
multi-hop, I don't think so.
Yeah.
There are some papers that
And given delay, would you go for if I have multiple origin destinations, would you care for multiple distribution delays or you will do that?
That's the Urbana-Champaign.
You give technical answers instead of philosophical answers.
Personal preference, right?
Yeah, what counts more?
No, but I mean, to put it to design a network or a policy, what would you go for?
Well, some people argue that equalizing delay makes sense if you're interested in things like
I'm assuming all the users the
minimizing
same.
jitter.
I'm assuming all the users the same, no preferential packages, no packages. So everything is more or less the same. What would you go for? So the only thing I'm trying to discriminate is the qualities of the paths.
I don't know if there's an answer to that one.
I don't know if equalizing delays on every link would produce equal end-to-end.
Is there some sort of principle here that people would like to use?
I'm not aware.
I'm not either. I've been trying.
Are you talking about equalizing delays on every link or not?
Maybe the delay is not very different.
On all paths,
Yeah,
on
all
the same
paths.
dissociation. Yeah, so there is this work by Kumar and Borka.
We know. But I mean, we know the result. The question is what will in the context of training throughput versus delay, what would you go
But
for?
how would you, like Tony said, I mean, you can't say because you have to, I mean, there is nothing that will give you the best delay. I mean, you can't have lexicographic type of result.
Multi-criteria.
Right. So you have to have some
But
links.
there is.
Unless you decide, you say that's what I want to do. To me, this counts on the sum of the groups and the sum of the delays.
Okay. Another question. So, could you use this to discover, following his line, discover other policies that they have the same problem?
I mean, I do believe so. I do believe so. So because
Using
the
the principle
Lyapunov,
that I'm trying to make the tool
it's
more
sort of like
efficient.
what people call control Lyapunov. You start off with some Lyapunov function, then you try to minimize its drift. My belief is that to try to minimize its drift, it also actually minimizes the expected value of the Lyapunov function in steady state. This is a conjecture. So I don't know.
You can go and analyze problems where you have a control mechanism.
Right.
Or just that you know.
Exactly.
And then
Exactly.
the control will be corresponding to the policy, and you can see it does the same thing.
Yeah.
I mean, trying to say.
I think so. I believe so. I don't know for sure.
Any other questions? Can I ask the experts another question now? Hello? I have, since I have the experts in the room, I have this following fundamental question, and maybe it's true. In all this max flow and all that, max weight and all the calculations and so forth, you never know the capacity when you start.
Capacity in the information theory.
No. Capacity reasons.
Stable, no, we don't know.
So what is the name of the theorem that says, if I am the capacity reason, this is okay?
Well, there are results
Forgive
that
for my
say
intrusion,
what happens and what you should do when you're outside the
You never know.
You don't know, but there are.
I keep asking these questions for experts.
But that's one
But
answer.
yes, you know, that's not another answer.
That will be doing the maximization.
Exactly.
Say what?
Yeah. So you do congestion control to bring yourself within the capacity.
But how do you know?
You don't know. You don't automatically does it right. That's the magic of congestion control. So
But I don't know.
How do you know when you're in it?
How do you know
you don't need to.
You don't. You just exercise controls for flow control. You observe the queue behavior.
Are you telling me I have to look at my route and should it blow up and stay?
In a way, you're keeping traffic outside if you're overloading the system.
We'll discuss this again.
Throttle it and.
I have you here, I need to clear that.
That sounds good, Mike.
A lot of results.
No, but there's if there also.
Yeah, but it's.
If you look, I mean, we had him here, right? Who was the guy? Niels, right? I asked him the same question, he kept saying, changing one if with another if.
There's no if there.
It's difficult because you cannot characterize fully all of the parameters that you need, but the idea is that I don't know where I am I stable or not? So I let traffic in, and then I observe the queue size, how they develop, and then I adjust.
Can I say how they grow, whether I'm getting near or not?
You don't.
There are results on that.
Because if I cannot do that, then it's
No,
useless.
you don't need to. All you need to do is as the queue length grows, you reduce your rate. That's it. This is the basic
Say
idea.
it again.
As the queue length grows, choose your arrival
No, you
rate.
have to tell me how much it has to grow and how much
It
I.
doesn't matter. Choose your arrival rate to be 1 over q. That works.
That's going to be very cool.
No. You can show that this actually maximizes.
No, but
So the answer to such policies.
the rate I allow is going to be small, that's why I'm
No,
going to do it.
it's not.
What if you use that?
But the queue is large.
the property of this is that if you're outside the region, then you say what happens. If you're inside the region, you say what happens. But this policy will work in both cases, whether you're in or out. So that's why you answer the question with ifs, because yes, you don't know.
The work means here what?
So you say I'm doing that, okay? I throttle the what I think based on
Right.
and then okay, you say what good is this policy? Then you say if I'm outside the stability region, then this will have this problem. If I'm inside, it has this problem. Both are good. They kind of do what you would like to do. So that's the kind of result you get.
Right, but you don't, it doesn't tell me how good of a throughput I get.
No, you do.
How good of a
Yeah, in fact, it precisely tells you this. It actually maximizes.
Maximize throughput.
Maximizes log of x subject to x.
Yeah, that's the utility demand. They never do maximization result.
Right. So this is not like, I think what you're saying is wrong, because the QM becomes large, x becomes small. But if x becomes small, the Q will become small again, and so it'll allow you to
Okay.
transfer it at a higher rate later. So on average, it's not always necessarily going to be small. It will of course be small if the number of users is large.
Okay. All right. Any other questions? All right. This time,